Welcome back to Let's Code. I'm Chris Biscardi, and I want to create particle system shaders for my video games, and I don't know how to do that. So I think that through a combination of compute shaders, vertex shaders, and fragment shaders, which 2 of 3 of those I have some experience with at this point, I can get that to work. So on the right-hand side here, we've got one of the Bevy examples that we're going to be going through today. And it is basically my introduction to compute shaders. We've seen vertex and fragment shaders on the channel before. Vertex shaders deal with particular vertices and points and mesh triangulation and stuff like that, whereas fragment shaders are more of the classic like color generation and pixel munging that you might see. We've also seen some post-processing shaders as fragment shaders in the 2D landscape, and compute shaders fit into all of that. So sometimes we want to do a calculation that doesn't require us to draw an image. In this case, we do draw an image. It's the game of life. But sometimes we want to do some calculation, maybe some noise generation, maybe, I don't know, something else. I'm sure there's other things to generate. But compute shaders are that. So this is kind of the very general version of shaders. And I'm going to run the compute shader right now. It's just a Conway's game of life. If you're unfamiliar with it, I believe the rules are there's a bunch of pixels here that are either turned on or turned off. And I think the rules are something like if there are 2 on pixels next to an off pixel, the pixel turns on in the next frame, and same thing to turn off. The rules don't really matter for us. It's not really important. But basically, we can use a compute shader to generate all of the different pixels. And this is a 4K screen, so you can see quite a few pixels here. And we can use buffers to interact with the computation that's going on here. So this is a way of generating data. And you can see how I might generate particles here instead of just a game of life representation. So I've got the code here already. I guess I will open all of Bevy because that seems to make the most. Let's bring this over onto its own desktop here. So in the examples folder, if we go down to shaders, we can go to the compute shader example, which is compute shader game of life. And I haven't done too much with this example yet. I took a look at it, but you know, I didn't read in too much into it. So this is going to be our journey into understanding what compute shaders do. Cow, something that I see here right away is copy on write, which we may or may not have to get into to describe some of this logic. We've got a size here that is 1280 by 720. We've got a work group size that is 8. So there's something with compute shaders where you want to batch up the work. So similar to the way that a fragment shader operates on fragments, and does that exceedingly parallelized, like does all of the fragments at the same time or something like that. Compute shaders can do the same thing. So we want to work in batches that work well for some kind of GPU node. And I think that's what this sizing is. I don't know how important the sizing is here. We clear the color. So background color, uncomment for unthrottled FPS. Let's do that for fun. So Bevy's window does VSync by default. And if we run the example with no frame rate lock, I have no idea how fast this is going to run. I have no idea if that's faster than before. I think the frame rate on this particular monitor is not that high. I think it only goes to 30 or 60 or something like that. So I'm not sure that this would have much of a difference. If I drop it on my 1080p monitor, it does run faster, but that doesn't necessarily mean anything. My 1080p monitor does have a frame rate of 244 hertz max or something like that. So I don't know. I don't know that this did anything. We might have to see a different example for that to be really apparent. We add the default plugins like we do for pretty much every Bevy application ever. And then we add this game of life compute plugin. And we have one startup system. So the game of life compute plugin is something that we are going to define because it's not imported here or anything like that. So let's start with the setup function. The setup function, this image is actually really interesting. It's one of the things that we saw in the post-processing example. So I'll link that video in the description. But basically, the last time we used this image type, we created an image, we passed it, or we rendered one of the 3D cameras into that image, and then passed that as a texture to a 2D camera to do the chromatic aberration post-processing. So images are just data that we can fill. And this is a recurring theme with shaders. We talk about things in very like, oh, RGBA. But really, this is just like a generic vec4. Like, I think RGBA 8U norm is 4 8-bit integers, unsigned integers. So exactly what we see here. So it's 0 to 255 4 times. So it's basically RGBA as you would be familiar with it in like CSS land or something like that. And extent 3D here is defining the size. So in this case, it's what, 1280 by 720. And then there's depth or array layers, which I've seen in, so we saw in the array textures video, we used the array layers. We had one texture that was 4 cubes that were arranged vertically. And then we were able to reinterpret the image as being layers. And we could pick a layer based on where we were and apply that to our cubes. So if you want to learn more about that, go watch the array textures cubes video. Texture dimension D2, I think we get D1, D2, and D3 here. Yeah, so we get D1, D2, D3. We don't get any other options. Texture view dimension is something different, but since it's different and not here, I won't mention it much more. It looks like we're creating a new image here and we're filling in effectively 0 values and then an alpha of 1 effectively. So 100% alpha. The texture descriptor is something we've also seen before. I don't really know how these flags are interpreted, but I believe these are bit representations of these different values. So we've got copy, destination, storage binding, and texture binding. So these are the ways that we can use the texture. And using the pipe is kind of ORing them together. So each of those has some bit representation like 0, 1, 0, 0, 0 or something. And we're just putting those all together in a compact way. So then we add images to our assets database for images so that it sticks around basically. Because remember, we're in the setup function and this function isn't going to run again. So we have to be able to query this from another system. And then we spawn a 2D sprite, which is the same size as the area that we're computing for the compute shader. So this is 1280 by 720. And this is the same approach that we saw in the post-processing, where we basically created like a 2D quad. So like a big square that matched the size of the camera 3D output. So we're basically drawing our image onto this buffer. So you can see the image is the texture for the sprite. And then we pass in the image into Game of Life and we insert the resource. So not 100% because we haven't seen it actually being used, but that's my guess. My guess is it's being used very similarly to the post-processing example where while we don't need to use compute shaders to do rendering, if we take this image and we update this image, this sprite will update with the output of our data. So yeah, I mean, it looks like we're rendering things here intentionally, but keep in mind that the compute shader is separate from the rendering. And this is just like something that happens to work easily for us to like show the output. So we've got our Game of Life compute plugin. This thing that we created, the Game of Life image, is a struct that is defined here. And you can see that it holds a handle to the image, which is what we gave it. And it derives this extract resource. And then we've got some bind group stuff, which we'll get into in a second. So bind groups are something that we've seen in all of the fragment shaders and stuff like that. There's a new derive called as bind group in Bevy 0.8 that's super useful. Got a bunch of videos using that. So this plugin is just a Bevy plugin, nothing special so far. This build gives us access to the app. If you've ever used like a Bevy plugin for physics, like the Rapier, the Bevy Rapier 2D or something like that. Plugins are the way that third-party crates can add themselves to your application to like start up different systems for physics and stuff like that. And now the comment here is extract the Game of Life image resource from the main world into the render world for operation on by the compute shader and display on the sprite. So we've got this extract resource plugin and we're adding it with kind of this type argument of Game of Life image, and we're setting it to the default. And I believe that there's a distinction between the code that runs on the CPU and the code that runs on the GPU. And there's a sort of a loading step that needs to happen. So if we have an image and it's in Rust land and it's got just a bunch of like numbers, zeros and ones and stuff, we have to encode that some way and load it onto the GPU. So I believe that this extract plugin is the thing that handles that functionality. If we copy this and I do a rip grep on the code base, let's do it inside of crates. We can see the extract resource plugin being used in quite a few places. Actually, only 5. 5 is not that many. It's less than I thought. And it's defined in Bevy render source extract resource. So let's go into the crate, Bevy render. Bevy render is where we spend most of our time. Source extract resource. Bevy render is the crate that we spend most of our time in when we're dealing with the fragment shaders or anything like that. So that's a interesting thing to know if you're ever looking for the WGSL scripts or anything like that we've used. And this says extract resource describes how a resource gets extracted for rendering. Therefore, the resource is transferred from the main world into the render stage extract. So this is a documentation link because we're working with the main branch. I'm not able to click on this, but there's something called render stage that is in this crate. And there's a render stage called extract, or with the extract label. And this deals with extracting some resource into the render world or the GPU at that time. So here's the plugin. It has basically the same description. It points to basically the same thing. So if I wanted to dive more into how this would work, I would go figure out more about the render stage, extract stage. Stages are how Bevy kind of organizes all of its code currently, or not code. Sorry. Bevy, or stages are how Bevy forces sync points for the commands that you use. So the only way to guarantee that a set of commands, such as spawning new sprites or something like that, has finished and succeeded is to detect that in the next stage. And Bevy has a number of different stages. There's a PR called stageless, so I'm not going to get too much into stages for fear that they are just going to get removed. But there's a package called IYes_loopless, IYES_loopless, that implements some of the inspiration from that PR. So that's something worth checking out if you're interested in that. So render app, we get a mutable sub app. And sub apps aren't something that I've gotten into in Bevy too much, but my understanding of them is that basically we can have like our Bevy game, and then we could have like a sub Bevy sub game happening inside of that. So that's what this is, I think. I don't know where render app comes from. Render app comes from render. So my guess is that sub app mute is grabbing the render sub app so that we can change things about it. And then we insert a resource that is the game of life pipeline, which is something that we haven't checked in yet. And then we add the system to the render stage queue with the queue bind group system. So this again is us getting a sub app, which is a unit of organization for Bevy. And we are inserting a resource, which we've done before. And we are adding a system to a particular stage, and that's the queuing the bind groups up to be sent across to the GPU, I would guess. Maybe render stage is something we want to actually look into. So if we are here, render graph, render phase, render resource, where's render stage? Render stage. So render stage is extract, prepare, queue, phase sort, render, or cleanup. And to get to this, I just went into the lib.rs for the render crate. So extract data from the app world and insert it into the render world. This step should be kept as short as possible to increase the pipelining potential for running the next frame while running the current frame. Interesting. It's really interesting that we basically like almost do advanced work. That's kind of fun. Prepare render resources from the extracted data for the GPU. So this is one of the ones that we were just looking at. Queue is where we just added our system. So this is where we create the bind groups that depend on the prepare stage data, and we queue up draw calls to run during the render stage. So that's the stage down here. So we basically prepare our data, then we create the bind groups. So I'm not sure why this is called queue. Maybe that's like standard terminology. I guess it's because we're queuing up draw calls. But in my mind, creating the bind groups is the thing that we're doing here. And then phase sort, which we haven't seen at all, so I'm not sure is super important. There's also a to do here. This could probably be moved in a favor of a system ordering abstraction in render. Okay, so we'll just ignore that for now. And then the actual rendering happens in render. In most cases, only the render backend should insert resources here, so we're probably not going to do anything to that. And then we clean up the render resources. So those are the stages that we run through for the render sub app. So we're adding to queue here. And I think we saw one other in here, didn't we? Oh no, we were dealing with the extract stage. So this extract plugin is adding this game of life extraction to the extract stage, which we then queue up, and then we deal with the render graph. So we get the render graph, which is a resource. We add a game of life node. So render graph is like, I think it's based on pet graph. I'm not sure. But basically we've got nodes and we've got connections or edges between those nodes, and we can store data in all of those places. So we add a node called game of life with the game of life struct default value. So you could think of this as being really anything. Like if this was labeled like lives for a game or something like that, then this could be 0 as the default value, right? It's just a label and a value. And then we draw a node edge from the game of life node to the camera driver, which is interesting. I don't know what that does. Presumably there's something inside of Bevy that traverses these edges, but I don't know where that code is. So maybe I will make a note to myself to look that up later. The other thing we could do is do another rip grep on crates for render graph. And like you could use grep or ack or whatever find functionality you want. I use rip grep because I use a lot of REST stuff. So render graph is used everywhere. Okay, here, Bevy render source render graph mod, but that's not where render graph is defined. But I think we could get there. So Bevy render, I forget what I said. Is it renderer, graph runner, graph runner? Graph runner is interesting. I think that's where the code would be. Render graph runner. Yeah, okay. So I don't know that we're going to dive into this right now, but there is a function inside of this that I just happened to find that is called run graph. And I assume that that is what traverses these nodes. And this code is probably super generic, so we probably won't see something like the camera node in here. But very interesting that we found that. So here's render graph right here. If we go to mod, where is render graph defined? Maybe in graph, edge existence. Oh, wow, this is a large comment. Here's the render graph. So we've got nodes, names, subgraphs, and the input node, and then some functions that render graph implements called update, set input, some other stuff. Let's take a look at this comment because this comment is probably going to tell us what the render graph actually is. The render graph configures the modular, parallel, and reusable render logic. It is retained and stateless, retained probably as opposed to immediate mode rendering. Nodes itself may have their internal state. Oh yeah, okay, so stateless, but nodes can have their own state. So the graph itself is stateless, but each node can control its own state, which cannot be modified while it's being executed by the graph runner. So this seems like a structure we build up and then execute and then maybe modify and then execute again. The render graph runner is responsible for executing the entire graph each frame. It consists of 3 main components: nodes, edges, and slots, just like we talked about. Slots are something that I didn't have the word for before. I've seen that mentioned. Nodes are responsible for generating draw calls and operating on input and output slots. Edges specify the order of execution and connect input and output slots together. And slots describe the render resources created or used by the nodes. So these seem like these are well defined. So a node will generate a draw call, an edge will specify the order of execution, and slots describe what resources are actually needed. Additionally, a render graph can contain multiple subgraphs, which are run by the corresponding nodes. So theoretically, if we needed to, we could insert a subgraph and have that like render as a child of this game of life stuff or something. Every render graph can have its own optional input node. And then it gives us an example. This example is likely to be very, very simple. Yeah, so basically we've got a node type. We've got this run function that we implement for node, which does something. It takes some arguments. So it gets the graph, it gets the render context, and it gets access to the world and has to return a result. And then we get to create the graph, add a couple nodes, an input node, an output node, and a node edge. And then we do nothing with it because it's a simple example. But yeah, so there is a render graph. That's what the render graph is. That's what's happening here. So to go over that again, we are setting up our image to be extracted in the extract stage of the render app. The game of life pipeline is instantiated inside of the render app, and we are queuing up bind groups inside of the queue stage, which is exactly what we're supposed to do in that queue stage, as we read before. And then we, in the render graph, when everything goes to render, we are inserting a node that is the game of life node and adding an edge to the camera driver. So presumably something happens from the camera driver to trigger the game of life or something like that. So moving on, we get the game of life image bind group. Bind groups contain the data that we send to the GPU, as far as I'm aware. Somebody else could probably explain that better. But we have this queue bind group function that gets commands the game of life pipeline resource, the GPU images. So instead of the assets database, we have the render assets database here, which should contain images. So it's a render assets database of the kind of image that we created earlier. Here is literally the game of life image itself. And then we get a render device. And this code right here is the lower level version of the as bind group generated code. So we talked about texture views before. In this case, I think this is going to end up being like a 2D texture. We create the bind group ourselves manually with this bind group descriptor struct. We specify the pipeline. I don't know what texture bind group layout is, but that's fine. We set up binding 0. So this is the ID that we would otherwise have as like a uniform or something like that. And then we bind the texture view to that 0 for our shader. And then we insert the game of life image bind group as a resource. So the pipeline takes the texture bind group layout, the initialize pipeline, and the update pipeline. Not sure that that's super interesting for us. There is quite a bit of code left here. So this pipeline is something that we create. From world is basically like the default inside of Bevy. So if you have to access other assets, you would implement from world for your type to instantiate the resource. So we use the world to get the render device resource. We create the bind group layout with a bind group layout entry with a binding of 0, visible to the compute shader stage with a type of storage texture. Again, the texture format is the RGBA8U norm, which is our vec4 of 8-bit values. And the view dimension is a 2-dimensional array. So we've got like X and Y values, basically. I'm not 100% on this, but I've seen it in exactly this setup in multiple ways. So I think this is just saying, hey, this texture is going to be visible by the compute shader. So our image, the thing that we're storing the data in, and then we are binding that as a texture in this format with this dimension. And then the shader is something that we load using the asset server. So this would be like an asset server.load shaders gameoflife.wgsl. So if we go to assets, because all those are in the root shaders, gameoflife.wgsl, we can see that the binding here is the texture storage 2D with the RGBA U norm with a read write. So we can read it and write to it. Whereas normally for uniforms, we would only be able to read. But this is exactly what we just set up. We set up this binding with that ID of 0 and describing it as this format. I don't really care that much about the actual game of life code. I think that there's some interesting things here, like the workgroup size is the size that we defined in Rustland. So instead of at fragment or vertex, this is at compute. Define a workgroup size, an initialize function, and some utility functions, it looks like. So these functions are just like functions that we defined. Oh, there's 2 workgroups. So init and update. So we probably get to define a 0 value here. This is setting up the data. And then we store that data in the texture. So the location is of x2. So we've set this image data, and you can think about it as like an XY grid. So at X and Y. So we've got an invocation ID that is probably like 00 or like 45 or something like that. That gives us the location in the texture to store our data. This is generating some random float, which who knows what random float does, or actually it does this, but it doesn't really matter. It's just some random number. And whether it's alive or not. So if the random number is greater than 0.9, we color it in. If not, then we don't. And then we store that data, that color, which is either black or white, in that location in our image. And that's what texture store is doing. So that initializes some randomized data into our image. And then update does the game of life logic. The game of life logic isn't super interesting. We got the workgroup size again. The invocation ID gives us our X and Y values for the location that we need to be processing. And then I don't know what storage barrier is. So that's something that I'm going to make a note of later. That seems important. Storage barrier is not something that we define here. So it has to be in the WGSL spec because we are not really importing anything. So let me do WGSL spec and storage barrier. And here's what storage barrier is. It's a synchronization feature. So storage barrier and workgroup barrier. all synchronization features execute a control barrier with acquire release memory ordering, that is yada, yada, yada. These are functions that can only be called in the compute shader stage. It affects memory and atomic operations in the storage address space. So maybe this is a way of basically doing like a transaction into that data. I think I'm going to have to read the spec a little bit more to really understand what this does. But they're effectively synchronization points, which makes me think like transactions or like atomic types or something like that. It does specify exactly what's going on here, but like that's something that I'm gonna basically skip understanding that at this point and go back to it later. And just know that this is kind of like we have to do the calculation. We have to like wait for something or do it this atomically. And then we store the new color at the same location that we were processing in the texture. So the WGSL isn't that complicated, but we load it in here. We grab the pipeline cache and we queue a compute pipeline with the compute pipeline descriptor struct, which uses our texture bind group layout, which we defined at the beginning of this function, which is just saying like, hey, we have a compute shader. It takes this data at binding 0. So remember, binding 0 is our RGB88U norm 2-dimensional image. So when you read it out like this, it's not that bad. It would be kind of confusing to figure this out from scratch without this example. So I'm glad this example exists. But we take the pipeline cache, we queue the compute pipeline with the layout that we have initiated. The entry point, I don't know why we do a copy on write for a string. Maybe we need to send this data to the GPU or something. I don't know. Shrug. But the entry point is going to be the init function. And then the update pipeline is going to be the update function. I wonder if we get to define as many of those as we want. So now if we look at the game of life pipeline, it makes more sense. The init pipeline is initializing all of our compute and the image, and our update pipeline is updating all of the positions in our image. And then we've got the texture bind group layout, which defines what kind of data we're sending over the pipeline. Our game of life state is either initialized, loading, or updating. Our node, so the node that we stuck in the graph earlier, is just game of life state, which is loading, init, or update. So not very complicated state. We're not storing like data in the node. We're just storing like what it's doing at a given time. It starts out by default in loading, and then we implement the render graph node for the game of life node, which sees us getting the game of life pipeline that we defined earlier with the pipeline cache. If the corresponding pipeline has loaded, transition to the next stage. So it looks like this value gets updated by Bevy in some way when it's doing the rendering. And we can detect what state that node is in, or maybe we are updating it. I don't know. I don't see where we are updating it, but let's do a copy, see if we can find this. Copy FV, and then look to see if we missed something. Doesn't look like it. Oh, there we go. We do set the state. So in our render graph implementation, which is what we were just looking at, if the state is loading and the cached pipeline state is okay, then we get the compute pipeline state for the init stage, and we set the state of the node in our graph to init. So we are controlling the lifecycle of the compute shader. Once we're in init, so this function presumably will run whenever there's an update to the render graph, that is. The game of life state in the initialized state, if we can get the pipeline state and it's okay, we get the update pipeline from the cache and we set the node state to update. So it looks like getting this from the cache does something in terms of like setting that to run. Pipeline cache, get compute pipeline state. So this is the interesting part. And this is the render graph update, and then the render graph run. I don't know what the relationship between update and run are, but presumably one runs at one point and one runs at another point. So in the run function for our node, which is the game of life node, we get the bind group layout. We get the pipeline cache again. So the pipeline cache seems to be super important to all of this. And then we get our actual pipeline resource. Remember, these are resources, so RES. And then we get the command encoder, and we begin the compute pass if we're running. So if we are in the run stage for this node, we begin the compute pass with the default compute pass descriptor. We set the bind group 0 to our texture bind group, which I believe includes our image. Select the pipeline based on the current state. So if we're loading, We don't do anything in run. If we are in the init state, then we need to initialize the actual pipeline. I don't know why we get compute pipeline state here. It looks like we just throw away the value. So this actually doesn't matter. It's just like making sure that we actually can get access to it before we set the state to the next thing. And then self.state in the init state, when we're running the node, we get the compute pipeline. In this case, we set the pipeline that we are running for the compute shader to the initialization, and we dispatch the work groups. So this is I'm still not sure how important these work group sizes are. But it looks like we are doing batches of pixels effectively for these work group size. So size over 8, and then 1. So the number of work groups for the X position and the Y position, or the number of pixels that get calculated by each work group. And then if we have updated to the update state, then we do effectively the exact same thing, and we dispatch the work groups to the update pipeline. So altogether, it's a lot of code. It's a lot of new names. It's a lot of new concepts. It's a lot of things. But the actual functionality, if we follow the example, doesn't turn out to be that complicated. We are basically creating this compute shader. We set up the way that we're going to transfer the data to the GPU. And then in any given place, we either initialize that data or we update that data. And then, of course, if we go back to our setup function, we've set up this sprite bundle to use the handle to the image that we are updating. So this image gets updated by all of that processing, and then the sprite displays it to us. So if we run this example again, we now understand what's happening here. So we've got a set of work groups. So we've got like an 8 by whatever square here that's getting processed. This whole thing that we are seeing here is our image. I think if I make this bigger, that's more clear. So it's a 1280 by 720 image that we've bound directly to this sprite. We do the processing in the compute shader, and then we get the output. And then presumably we can do whatever we want with that output. Although in this case, all we're doing is displaying it. So I hope that helped if you're interested in compute shaders and Bevy. This was the first time I've ever been through that example. So eventually I'll probably have a video on like what a compute shader actually is and how to use them. That isn't just running through the Bevy example. But I hope this helped. I hope you enjoyed it. And hopefully we'll get a physics system in a future video. And I'll catch you next time.